hope you have had a chance to view my videos that introduce the fundamentals of chemistry. In my prior video, I talked about how batteries work. In this video, I will talk about fuel cells. Fuel cells are very much like batteries, except the chemical energy can be continually replaced with new fuel. Fuel cells have anodes, cathodes, electrolytes, and separator components just like batteries. Fuel cells convert chemical energy directly into electricity just as batteries do. The difference between batteries and fuel cells is that batteries have all their available chemical energy sealed inside. Fuel cells usually have an external plumbing system and venting system so that fuel and oxygen can be brought inside and exhaust can be expelled. Theoretically, a fuel cell could produce electricity continuously as long as it receives fuel and oxygen. In reality, a fuel cell may run continuously for a few years until its components, electrolyte, and separator and seals degrade, corrode, or leak so badly that its performance decline to a point where it's not worth keeping in operation. The conditions inside a fuel cell can be so harsh that even high-grade stainless steel rusts and dissolves. So before one chooses a fuel cell over other forms of electrical generation, one must do a cost-benefit analysis to be sure that the life of the fuel cell is long enough that savings from its efficiency in electricity production over the fuel cell's lifespan offsets the high initial cost over other alternative forms of electrical generation. Fuel cells are not as portable as batteries, although some fuel cells have been used to power automobiles and smaller vehicles such as golf carts and fork trucks. There are fuel cells that are light enough to power drones. A battery-powered vehicle might take many minutes or hours to recharge. A fuel cell-powered vehicle can be refueled as quickly as a gasoline-powered vehicle. At their current state of development, fuel cells are too large to power handheld electronic devices. On the large end of the scale, stationary fuel cell power plants have been built that weigh many tons and concede 5 megawatts of continuous power. Whole farms of stationary fuel cell power plants have been built in South Korea that can compete with wind farms of wind turbines or solar farms of solar arrays in electrical power output. In Japan, as of 2018, E&E Farm has installed over 265,000 0.3 to 1 kilowatt sized fuel cells into residential homes to suit the homeowners' electrical needs. These residential fuel cell units get their fuel from LP tanks or straight from the natural gas lines in the street. Essentially, these residencies are exchanging the electrical grid for the natural gas grid. The electrical efficiency of these stationary units is 60%, nearly double the efficiency of the electrical grid. Fuel cells run at much higher temperatures than batteries. Alkaline fuel cells and PEM fuel cells run at the temperature near the boiling point of water, or around 100 degrees Celsius. Solid oxide fuel cells, or SOFCs, can run at temperatures over 900 degrees Celsius. The excess heat generated by high-temperature fuel cells can have cogeneration uses, such as heating buildings or heating ovens to produce products, and even baking bread. In hybrid electrical systems, the fuel cell generates electricity directly, and the excess heat is used to power a turbine that turns a secondary electrical generator. Many, but not all, fuel cells use hydrogen as fuel. In itself, hydrogen is more of a store of energy than a source of energy. There are no great reserves of naturally occurring hydrogen on Earth. Hydrogen gas can be extracted from water by electrolysis. Electrolysis is sending electricity through H2O to break up the hydrogen-oxygen bonds. Electrolysis of water wastes electricity, as the fuel cell that used the hydrogen to make electricity will never make as much electricity as was used to extract the hydrogen from the water to begin with. If the electricity came from a green source like solar panels or wind turbines, storing that electricity as hydrogen fuel could be partially justified. If the source of that electricity is fossil fuel, storing that electricity as hydrogen is not justified. Hydrogen can be reformed from fossil fuels. Methane, CH4, the major component of natural gas, can be easily reformed from methane into hydrogen and carbon dioxide using catalyst. Methane to hydrogen reforming is an endothermic reaction, which means that the reforming process absorbs heat. The heat can be provided by the fuel cell. In fact, there are fuel cells that use internal reforming to cool the fuel cell so that it does not overheat. By chemical manipulation, diesel fuel and coal gas can be processed into methane that in turn can be reformed into hydrogen for use in fuel cells. Reforming fossil fuel into hydrogen is partially justified because fuel cells can be twice as efficient at converting fuel into electricity as diesel or gasoline-powered electric generators. Large gas turbine-powered generators can be made as efficient as fuel cells. If the source of methane fuel is biomass, such as food waste, garbage, or sewage rather than fossil fuels, then reforming the biomethane into hydrogen for use in fuel cells provides a very green source of electricity. Storing hydrogen can be problematic. Hydrogen gas molecules are tiny and will slip through the tiniest crack in a tank or will leak through seals that would easily hold back larger molecules. Hydrogen gas can also cause hydrogen embrittlement in steel tanks. Hydrogen atoms embrittle steel by wedging themselves in between iron atoms, resulting in an interstitial alloy that cannot stretch and so may crack under pressure. Steel tanks that must hold hydrogen must be made extra thick as a precaution against embrittlement. One way to take advantage of hydrogen's small size is by deliberately storing it in containers of porous material that allow the hydrogen to reside interstitially or between larger molecules until they are needed. Metal hydrides have been used in fuel tanks. On the slide, I list some common metal hydrides. These metal hydrides absorb and bond with the hydrogen until it is needed. In some lucky cases, a small amount of heating or pressure reduction will drive the hydrogen out of the metal hydride so that it can be used. Research on metal hydrides for hydrogen storage continues. If the fuel cell unit has a methane to hydrogen reformer, the hydrogen can be stored as methane until needed. Just remember, methane reforming produces both hydrogen and carbon dioxide, so storage as methane is not carbon-free. There are several different types of fuel cells, including alkaline fuel cells, AFCs, proton exchange membrane fuel cells, also called PEM fuel cells, phosphoric acid fuel cells, PAFCs, molten carbonate fuel cells, MCFCs, and solid oxide fuel cells, SOFCs. I will examine the operation of these different types of fuel cells individually. I want to go back in history to the origins of the fuel cell. An early fuel cell is Grove's gas voltaic battery. In 1842, scientist William Robert Grove conducted experiments in a device in which he proved that electrical current passed through a bath of sulfuric acid could separate steam into hydrogen gas and oxygen gas. When Grove allowed the hydrogen and oxygen in his device to recombine back into water, the device produced electricity. Grove called his device a gas voltaic battery. Grove's gas voltaic battery is recognized as the first fuel cell. Grove demonstrated his gas voltaic battery to the famous scientist Michael Faraday. Grove also demonstrated his gas voltaic battery to science editor Edward William Brayley. Brayley published the results of Grove's work, which is why we know the story. The first commercial fuel cell was an alkaline fuel cell, an AFC, developed in 1932 by English engineer Francis Thomas Bacon. In the 1960s, NASA began using AFCs as the main source of electrical power on spacecraft, starting with the Gemini space capsules and continuing all the way to using AFCs on the space shuttle. The use of hydrogen fuel cells on board spacecraft was practical because spacecraft rocket engines are generally powered by liquid hydrogen and liquid oxygen, so hydrogen and oxygen were readily available for use on the spacecraft fuel cells. The parts of an alkaline fuel cell are the same as for a battery: an anode, cathode, electrolyte, and separator. Fuel cells have extra plumbing and venting components for bringing in fuel and oxygen and for exhausting the waste. The key of alkaline fuel cells is an electrolyte made from a gel of alkali metal hydroxide such as lithium hydroxide, sodium hydroxide, or potassium hydroxide. The alkaline fuel cells on the Apollo spacecraft and the space shuttle used asbestos separators sprayed with potassium hydroxide. The electrolyte separator is porous to allow the flow of hydroxide ions. The separator blocks the flow of electrons and forces electrons to take the wire path through the load placed between the anode and the cathode terminals. The electrolyte is coated with a thin layer of platinum catalyst or has a carbon layer embedded with tiny platinum particles. The platinum is the most expensive component of the fuel cell. The platinum catalyst is necessary to ionize the hydrogen on the anode side and the oxygen on the cathode side so they can react as ions through the electrolyte. No catalyst, no reaction. In operation, hydrogen gas is pumped into the anode side. The hydrogen gas dissociates into H+ ions and electrons on contact with the platinum catalyst. The H+ ions attract the hydroxide ions moving through the electrolyte and bond with them, forming water steam that is then exhausted from the anode. The electrons are forced out of the anode terminal by the negatively charged OH ions that are coming through the electrolyte. The anode half-cell reaction is 2H2 plus 2 hydroxides react to form 2 H2Os plus 2 electrons. The electrons travel the path from the anode terminal through the load and then into the cathode terminal. On the cathode side, the 2 electrons coming into the cathode terminal react with oxygen and steam entering through the cathode gas inlet. The reaction produces hydroxide that travels through the electrolyte onto the anode side to repeat the cycle. The cathode half-cell reaction is shown. O2 plus 2H2O plus 4 electrons react to form 4 hydroxides. The net reaction of the alkaline fuel cell is just a water formation reaction. O2 plus 2H2 react to form 2 H2Os. So, 2 molecules of excess water are produced for every 2 molecules of hydrogen. This water must be exhausted from the system. The water is so pure, the astronauts use the wastewater for drinking on board the fuel cell electrified spacecraft. On board the spacecraft, the fuel cell runs on the liquid hydrogen and liquid oxygen inside the propellant tanks. On the ground, an alkaline fuel cell can run on carbon scrub purified air. The nitrogen in the air will not participate in the cathode reaction. If carbon dioxide is left in the air, the CO2 will poison the alkali hydroxide electrolyte. For example, if potassium hydroxide is used as the electrolyte, the carbon dioxide would react to produce potassium carbonate. The potassium carbonate will plug the electrolyte pores and block the flow of hydroxide ions. The potassium carbonate cannot be removed, and sufficient carbonate poisoning will degrade the alkaline fuel cell performance or stop the fuel cell from operating. Next, we will look at PEM fuel cells. The PEM and PEM fuel cells can stand for proton exchange membrane or polymer electrolyte membrane. The major action in PEM fuel cells is that hydrogen ions or protons pass from the anode to the cathode through a polymer separator. As proton implies, PEM fuel cells use hydrogen for fuel. On the cathode side, the oxygen can be pure oxygen or it can come from air pumped into the fuel cell. The exhaust product is water. PEM fuel cells are the most compact fuel cells. Automobiles, forklifts, golf carts, and even drones have been powered by PEM fuel cells. PEM fuel cells operate at relatively low temperatures between 50 Celsius and 90 Celsius. The 90 Celsius higher operating temperature is dictated by the melting point of the polymer membrane. The most widely used polymer membrane material is Naflon, a brand name polymer produced by the Chemours company. Chemours was once part of chemical giant DuPont, but spun off as an independent company in 2015. The Naflon membrane is non-conductive and blocks electron flow, but allows H+ ions or protons to pass through it. One downside of Naflon is its maximum allowable operating temperature of 90 Celsius. Above 90 C, Naflon melts. Research is being conducted on polybenzimidazole ionomer, or PBI. PBI has a chemical formula C20H12N4. A PBI membrane may allow PEM fuel cells to operate at 220 degrees Celsius. A higher operating temperature is desirable so that the fuel cell can operate completely with steam to prevent problems associated with liquid water collecting inside the PEM fuel cell. Also, a higher operating temperature will allow more flexible cooling systems than the current cooling systems that are required to keep the membrane below 100 degrees Celsius. The operation of PEM fuels is similar to alkaline fuel cells, except the ions exchanged in PEM are H+ ions rather than hydroxide ions of the alkaline fuel cells. The parts of a PEM fuel cell are the same as for a battery: an anode, a cathode, an electrolyte, and a separator. All fuel cells have extra plumbing and venting components for bringing in fuel and oxygen and for exhausting the waste. The separator in a PEM fuel cell is a Naflon polymer membrane. The polymer membrane blocks electron flow and forces the electrons to take the wire path through the load placed between the anode and the cathode terminals. The Naflon electrolyte allows the H+ ions or protons to pass through it. Naflon is sulfonic acid bound to tetrafluoroethylene, TFE. Naflon has the chemical formula C7H-F13O5S-C2F4. It is that lone H that disassociates from the sulfonic acid and makes the Naflon a great transmitter of H+ ions. The polymer membrane is covered on both sides by a carbon layer of embedded platinum particles. The platinum is the most expensive component of the fuel cell. The platinum catalyst is necessary to ionize the hydrogen on the anode side and the oxygen on the cathode side. In PEM fuel cell operation, hydrogen gas is pumped into the anode side. The hydrogen gas dissociates into H+ ions and electrons on contact with the platinum catalyst. In the PEM fuel cell, the H+ ions dissociated in the anode pass through the polymer membrane to the cathode side, where the oxygen and electrons are waiting for them. The anode half-cell reaction is H2 reacts to form 2 protons and 2 electrons. The electrons travel the circuit from the anode terminal through a load to the cathode terminal. Where they enter the cathode, they react with oxygen and pull H+ ions through the polymer membrane. In the cathode, the electrons, H+ ions, and oxygen bond to form water steam that is exhausted from the cathode outlet. The cathode half-cell reaction is 2H+ plus O2 plus 2 electrons react to form H2O. So 1 molecule of water is produced for every molecule of hydrogen. This water must be exhausted from the system. I show an example of a PEM fuel cell in operation. The structure of a single PEM fuel cell has 11 layers of components. The 11 layers are: 1. A compression plate. 2. A cooling jacket. 3. The anode current collector, or ACC. 4. The anode bipolar plate, or ABPP. 5. A platinum embedded carbon catalyst layer. 6. The polymer electrolyte membrane. 7. A platinum embedded carbon catalyst layer. 8. The cathode bipolar plate, or CBPP. 9. The cathode current collector, or CCC. 10. A cooling jacket. And 11. A compression plate. The polymer membrane exchanges the protons. The platinum carbon catalyst layer allows gas diffusion, and exposure to the catalyst causes reactions. The bipolar plates accept the fuel and air inlets. The BPPs are grooved or serpentine milled on the side facing the catalyst layer to expose the gases to the catalyst. The BPPs have outlets to allow excess air and steam water products to be exhausted. The current collectors collect the electrons on the anode side and distribute the electrons on the cathode side. The tips of the current collectors serve as the positive-negative terminals that are wired through the load. Another cooling jacket layer is placed after the cathode current collector. Cooling fluid is run through these cooling jacket layers to regulate the temperature. The polymer membrane temperature must be kept below its melting point. A second compression plate is placed at the opposite end of the fuel cell. The fuel cell is squeezed between its 2 compression plates with insulated bolts or insulated threaded rod with nuts at each end. The compression ensures good electrical contact between layers and that no gases leak out of the fuel cell. The polymer membrane is a good electrical insulator to keep the positive and negative half cells from exchanging electrons except through the negative and positive terminals. I show the 11 layers of a single PEM fuel cell in the exploded view. The voltage across the terminals of a single PEM fuel cell is only 1.2 volts. To increase the voltage, the fuel cells are stacked in series to create a fuel cell stack. A 3-cell stack will have 3.6 volts across the outermost terminals. A 100 fuel cell stack will have 120 volts across the outermost terminals. The electricity produces DC current. A 3 fuel cell stack is shown on the figure. All it is needed to add fuel cells to the stack is to repeat components 2 through 9 of a single fuel cell. The current collectors, components 3 and 9, might not be necessary except at the ends of the stack where the terminals need to be connected to wiring. The plumbing to bring in cooling fluid, fuel, and air is not shown on the figure. The simplicity of PEM fuel cells make them the most common type of fuel cells to power vehicles and residential homes. The major drawbacks of PEM fuel cells are 1. The availability of hydrogen. 2. The high cost of platinum catalyst. 3. Catalyst poisoning by carbon monoxide. And 4. Temperature limitations of the polymer membrane. No large natural reserves of hydrogen are known to exist on Earth. The 2 major methods of making hydrogen are electrolysis of water and methane steam reforming. In electrolysis of water into hydrogen, DC electrodes are placed in water. Some type of electrolyte must be dissolved into the water to allow the current to flow between electrodes. The electrolyte might be salt, or an acid like HCl, or an alkaline base such as NaOH. When a DC current is fed into the electrodes, hydrogen gas forms at the cathode, and electrolyte-dependent gas or ions form at the anode. The hydrogen gas bubbles to the surface on the cathode side where it is collected. If the electrolyte is salt, NaCl, chlorine gas forms at the anode. The chlorine gas should be collected as it is poisonous. The hydroxide ions transfer through the electrolyte from the cathode to the anode side. The anode half reaction is 2Cl- react to form Cl2 gas plus 2 electrons. The cathode half reaction is 2 H2O liquids plus 2 electrons react to form 2 hydrogen gas plus 2 hydroxide ions. The salt solution electrolyte might include side reactions at the cathode. Chlorine gas plus 2 sodium ions plus 2 hydroxide ions react to form NaCl plus NaClO plus H2O. Electrolysis in salt is problematic due to its corrosive effects or oxidizing effects on the metal components of the electrolysis cell or deposition of impurity solids on the electrodes. If the electrolyte is an acid like HCl, oxygen gas forms in the anode. The oxygen can be collected or released straight into the air. The H+ ions transfer through the electrolyte from the anode to the cathode side. The half reactions are as follows. The anode half reaction is 2 H2Os react to form oxygen gas plus 4 protons plus 4 electrons. The cathode half reaction is 2 protons plus 2 electrons react to form hydrogen gas. If the electrolyte is an alkaline base like NaOH, oxygen gas forms at the anode. The oxygen can be collected or released straight into the air. The hydroxide ions transfer through the electrolyte from the cathode to the anode side. The half reactions are as follows. The anode half reaction is 2 hydroxide ions react to form 1/2 oxygen gas plus H2O plus 2 electrons. The cathode half reaction is 2 H2O liquids plus 2 electrons react to form 2 hydrogen gas plus 2 hydroxide ions. In all 3 electrolytes, the hydrogen gas bubbles to the surface where it can be collected. The major drawback of electrolysis is the amount of energy used is more energy than is stored in the hydrogen gas. Electrolysis of water to produce hydrogen is not justified unless the source of electricity is solar or wind or maybe hydroelectric. For special purposes, such as the use of hydrogen in spacecraft, the high cost of the hydrogen produced by electrolysis is absorbed in the overall budget of the space project. Methane and steam can be reformed into hydrogen by using a reformer. The methane can come from fossil fuels or biomass. The reformer uses catalysts and high temperatures to cause the methane and steam to react to produce hydrogen and carbon dioxide. The carbon dioxide must be scrubbed from the reforming products before the hydrogen can be stored. The reforming reaction is 2H2O plus CH4 reacts to form 4H2s plus CO2. Again, the heat energy required is costly. The heat produced by high-temperature fuel cells such as solid oxide fuel cells or molten carbonate fuel cells is great enough that hydrogen reforming is practical. If the hydrogen is for PEM fuel cells, the heat required for reforming is still a net profit if the CO2 produced is not a consideration. Electricity produced from a PEM fuel cell is still double that produced by a methane-burning internal combustion engine used to drive a small electric generator. The double figure assumes a PEM power conversion efficiency near 50%. If the source of methane is biomass, the CO2 production is neutral, as the carbon is already part of Earth's environment or Earth's carbon cycle. There are also problems with storing hydrogen. H2 molecules are tiny. They leak through small cracks and through most seals. Hydrogen embrittles steel by interstitial alloying with it. Pressurizing hydrogen is problematic. It blows by piston rings and embrittles pistons and compressor cylinder walls. Metal hydrides look promising, but a lot of research needs to be done to make metal hydrides practical for use. Platinum is the most expensive part of a PEM fuel cell. Temperatures are so low in a PEM fuel cell that the only known catalyst that can ionize hydrogen gas is platinum. Platinum is hugely expensive, more expensive than gold. Efforts are underway to reduce the amount of platinum needed in PEM fuel cells. Even if the platinum particles start out with a very small size, the platinum particles tend to migrate together and merge together into larger particles as the catalyst ages. Solutions include reducing the size of platinum particles to increase their surface area. The larger platinum particles reduce the catalyst surface area. Experiments are underway to discover a substitute material for platinum, but so far, no substitute is practical at the low temperatures that PEM fuel cells operate. Catalyst poisoning from carbon monoxide is a problem, especially for hydrogen reformed from methane. Carbon dioxide and carbon monoxide scrubbers are important. Catalyst poisoning is accelerated if the carbon monoxide in the hydrogen fuel exceeds 10 parts per million. Low temperature is also a drawback for operating PEM fuel cells. Naflon, the most common polymer membrane material, melts above 90 degrees Celsius. PEM fuel cells require a sophisticated cooling apparatus. Liquid water must also be removed from the cathode before it floods the electrolyte. Higher temperature polymer membranes are under development. Polybenzimidazole, or PBI, shows promise as a substitute for Naflon. PBI-based membranes can be used at temperatures up to 220 degrees Celsius. A high-temperature PEM fuel cell running above 200 degrees Celsius would be able to run completely with steam and avoid liquid-water problems. High-temperature fuel cells would also require less cooling because of better heat transfer with a higher temperature difference between the fuel cell coolant and the ambient environment. Efficiency would also be improved with higher temperature operation. An advantage that lower temperature fuel cells have over high temperature fuel cells is that low temperature fuel cells can use rubber seals and gaskets. High temperature fuel cells must rely on metal-to-metal seals or ceramic gaskets that are much more subject to cracking and leaks than rubber seals and gaskets. Next, I want to cover phosphoric acid fuel cells. Phosphoric acid is another type of electrolyte for use in fuel cells. Fuel cells that use phosphoric acid for their electrolyte are called phosphoric fuel cells, or PAFCs. The PAFC transfer ion are H+ ions, the same transfer ions as PEM fuel cells. The phosphoric acid electrolyte is embedded in a silicon carbide matrix. The chemical formula for phosphoric acid is H3PO4. Phosphoric acid is solid up to its melting point of 42 degrees Celsius. Above its melt temperature, phosphoric acid can lose one or all of its hydrogen atoms as H+ ions. This ability to lose its H+ ions makes phosphoric acid a good conductor of H+ ions in fuel cells. As phosphoric acid is solid up to 42 degrees Celsius, the PAFC must be warmed to this temperature, greater than 42 degrees Celsius, for its electrolyte to melt and begin producing electricity. The PAFC must be maintained at a temperature above 42 degrees Celsius to prevent the phosphoric acid from solidifying and damaging the platinum-embedded carbon catalyst layers on either side of the electrolyte matrix. The anode and cathode half-cell reactions of a PAFC are the same as PEM fuel cells. In PAFC operation, hydrogen gas, H2, is pumped into the anode side. The hydrogen gas dissociates into H+ ions and electrons on contact with the platinum catalyst. The H+ ions dissociated in the anode pass through the phosphoric acid electrolyte into the cathode side where the oxygen and electrons are waiting for them. The anode half-cell reaction is H2 dissociates into 2H+ and 2 electrons. The electrons travel the circuit from the anode terminal through the load to the cathode terminal. The electrons enter the cathode, react with the oxygen, and pull the H+ ions through the phosphoric acid electrolyte. In the cathode, the electrons, H+ ions, and oxygen bond to form steam that is exhausted from the cathode outlet. The cathode half-cell reaction is 2H+ plus half O2 plus 2 electrons reacts to form H2O. So, 1 molecule of water is produced for every molecule of hydrogen. This water vapor must be exhausted from the system. The PAFC operating range is 150 to 200 degrees Celsius. This operating temperature allows the water to be produced completely as steam. There are no problems with liquid water in PAFCs as there might be in lower temperature PEM fuel cells. PAFCs have a higher tolerance for carbon dioxide and carbon monoxide than PEM fuel cells. PAFCs can tolerate carbon monoxide levels up to 1% or 10,000 parts of CO per million parts H2 in fuel without accelerated catalyst damage or performance degradation. Some drawbacks of PAFCs are corrosion, catalyst poisoning, expensive catalyst, and maintaining a temperature above 42 degrees Celsius. Both carbon monoxide and sulfur can poison catalyst. The phosphoric acid is corrosive and will degrade the electrodes. Tracking studies done by Doosan UTC show that a voltage output of a 200 kilowatt PAFC power plant will degrade by 15% over a 5-year lifespan. PAFCs use expensive platinum catalyst. The platinum catalyst is the most expensive component of the PAFC. In the slide, I show a working diagram of a PAFC is the same as a PEM fuel cell. The only differences between a PAFC and a PEM fuel cell are the electrolyte and the working temperature. A single-cell PAFC has the same 11 components as a PEM fuel cell. The voltage across the terminals of a PAFC single cell is 1.15 volts. This is a little less than the PEM single cell voltage of 1.2 volts. The reactions are the same in both fuel cells, but the electrical resistance across a PAFC may be a little greater than that of a PEM fuel cell. To increase the voltage, a PAFC may be stacked in series. Every additional cell in the stack increases the voltage by 1.15 volts. So, a 100-cell PAFC stack will have a voltage at about 115 volts. Phosphoric acid fuel cell stacks have been used in stationary commercial power plants since the 1970s. The 150 to 200 degrees Celsius working temperature of a PAFC fuel cell stack means there's a moderate amount of excess heat available for heating buildings where they are installed. Stationary PAFC power plants are currently being built by Doosan Fuel Cell Company in the United States and by Fuji Electric in Japan. The Indian Navy has installed PAFC power plants in their Calvary-class submarines. And that concludes my discussion of low-temperature fuel cells. Thank you for watching. If you enjoyed this video and want to help me make similar content, please like and subscribe.